Hi there, and welcome to this lesson on Further Pure Mathematics 3. And in this lesson, we're on Chapter 1, 1.4, and hyperbolic identities and equations. We'll go straight into an example. Using the exponential definitions of sine and cos, prove the hyperbolic identity cos squared x minus sine squared x is equal to 1. No tricks or catches here. We're just going to substitute in for sine x and cos x and show that we get 1 for the answer. I'll let you have a go at doing that. Pause the video, come back to me when you're ready. Okay, let's have a look. So we're going to substitute in for cos x and sine x, which gives us that. Squaring the brackets gives us that. And the e to the 2x here and the e to 2x here will cancel. Same with the e to the minus 2x's. So we'll just be left with 2 over 4 plus 2 over 4, which does equal 1. And that's the identity proved. Example 2. Using the exponential definitions of sine and cos again, this time prove that cos 2x is equal to 2 cos squared x minus 1. Same method as before. I would start with the right-hand side and prove that it's equal to the left-hand side. It's slightly easier to do that. Anyway, have a go yourself, pause the video, come back to me when you're ready. Okay, let's have a look. So starting with the right-hand side, 2 cos squared x minus 1, substituting in cos x will give us that, squaring the bracket gives us that, cancelling the 2 and the 4 gives us that, and changing the minus 1 into 2 over 2 allows us to add the fractions together. On the numerator, we'll have a plus 2 and a minus 2 that cancel with each other, so we'll be left with e to the 2x plus e to the minus 2x divided by 2, which is the definition of cos 2x. So that is the identity proved. Now, trigonometric identities and hyperbolic identities, they are extremely similar to each other. Sometimes they're the same, sometimes they're just very close. So for example, cos squared plus sine squared equals 1 becomes the hyperbolic identity cos squared minus sine squared equals 1. Sine 2 theta equals 2 sine theta cos theta doesn't change at all. It just becomes sine 2 theta equals 2 sine theta cos theta. 1 plus tan squared equals sec squared does change. The plus changes to a minus, and we get 1 minus tan squared theta is equal to sec squared theta. Now, how do we know how an identity is going to change? Thankfully, there is a very easy method. If you know a given trigonometric identity, it's possible to work out the corresponding hyperbolic identity by using Osbornes Rule. There are 2 steps to Osbornes Rule. The first is quite simply replacing the given trig function by its hyperbolic counterpart. So cos changes to cos, sine changes to sine, sec changes to sec, and so on. But it's the next thing that is more significant. If you ever have a product or an implied product of 2 sines, you have to multiply the term by minus 1. What does that mean? It means if you had a term sine squared in the trig identity, that'll change to minus sine squared in the hyperbolic identity. Similarly for tan squared will change to minus tan squared because tan's defined in terms of sine. Tan squared equals sine squared over cos squared. So there's an implied product of 2 sines in tan squared theta. Same thing for cosec squared. That'll change to minus cosec squared because cosec is 1 over sine. And if you look at these 3 identities up here, you can see how that works out in practice. So the sine squared has to change sine. It becomes minus sine squared. There are no products of sines in the second identity, so there are no issues there. In the third one, tan squared has to change to minus tan squared because tan squared is sine squared over cos squared. Sec squared doesn't have to change because sec is 1 over cos, so it just changes to sec squared theta. Okay, I'll let you have a go at using Osbornes Rule yourself. So example 3, using Osbornes Rule, write the hyperbolic identity that corresponds to each of these trig identities. None of these take very long. I'll let you have a go at doing them yourself first. So pause the video, have a go, and come back to me when you're ready. Okay, let's have a look at these. So number 1 was cos 2a equals 1 minus 2 sine squared a. The hyperbolic equivalent of that is cos 2a is equal to 1 plus 2 sine squared a. Product of two signs there, so the minus has to change to a plus. Second one, cos 2a is equal to 2 cos squared a minus 1. The hyperbolic equivalent of that is cos 2a is equal to 2 cos squared a minus 1. Nothing has to change because there are no products of signs. And the third one, tan 2a is 2 tan a over 1 minus tan squared a. The only place we've got a product of signs is implied here in the tan squared, sine squared over cos squared. So the minus changes to a plus, and we get tan 2a is equal to 2 tan a over 1 plus tan squared a. Okay, example 4. Given that sin a is equal to 5 over 12, use the appropriate hyperbolic identity to find the exact values of cos a, tan a, and sin 2a. Now, none of these are too difficult if you use the right identity. But I'll let you have a go at working that out yourself. So pause the video, see if you can make sense of this, and then come back to me when you're ready. Okay, let's have a look. So the first one, cos a. I think the easiest way to do this is using the identity cos squared minus sin squared equals 1, and then substituting in for sin squared, which gives us cos squared minus 5 over 12 squared is equal to 1. Moving the 5 over 12 to the other side, and then adding those terms together, gives us cos squared a equals 169 over 144. Square rooting that gives us cos a is equal to 13 over 12. Now the second one, tan a, it's easy to forget this, but the easiest way to do it is just to remember that tan a is sin a over cos a. Sin a we know from the question, cos a we just worked out in the previous question. Substituting both of those in gives us 5 over 12 over 13 over 12, which gives us 5 over 13 for tan a. Sin 2a, well, using the double angular formula for sin, gives us sin 2a is 2 sin a cos a. We know both of these things. We can substitute both of them in. That gives us 2 times 5 over 12 times 13 over 12, which simplifies to 65 over 72. Okay, example 5. Solve 3 sin x plus 2 cos x equals 4, giving your answer in terms of natural logarithms. Now, I'll give you the first line for this, just so that you get started in the right direction. The easiest way to do this question is to rewrite sin and cos in terms of their exponential definitions, then to create a quadratic equation in e to the x, and to solve that. Okay, I'll let you have a go at working your way through it from here. So pause the video, have a go, and come back to me when you're ready. Okay, let's have a look. Multiplying out the brackets gives me that. Collecting together terms gives me that. Multiplying by 2 to get rid of the fractions gives me that. And then as before with this type of equation, we multiply through by e to the x, which gives us 5e to the x squared minus 8e to the x. E to the minus x times by e to the x is just e to the 0, which simplifies to 1. And then we have a quadratic in e to the x. It doesn't factorize. We'll need to solve this using the quadratic formula, which gives us e to the x is equal to 8 plus or minus this square root over 10. And that gives us e to the x equals 4 plus or minus root 21 over 5. Now, 4 minus root 21 would give a negative value for e to the x. But e to the x is always positive. So at this point, we can say that there is only one solution, which is that e to the x equals 4 plus root 21 over 5, and then taking logs of both sides gives us x equals the log of 4 plus root 21 over 5. Example 6. Using cos squared x minus sin squared x equals 1, and r sin x is equal to the log of x plus the square root of x squared plus 1. Solve the equation 9 cos squared x minus sin x equals 17, giving your answer in terms of natural logarithms. Now they've told you what to use, so we're going to change the cos squared here into 1 plus sin squared. We'll then get a quadratic equation in sin x. that does factorize. You'll get the two solutions and then use this to get the answer in terms of natural logs. Okay, I'll let you have a go at working your way through the whole thing. So pause the video, have a go, and then come back to me when you're ready. Okay, let's have a look. So using the hyperbolic identity for cos squared gives us that. Multiplying out the brackets gives us that. Tidying it up gives us that. And that does factorize into 3 sin x plus 2 times 3 sin x minus 4 is equal to 0, which has two solutions, sin x equals minus 2/3 or sin x equals 4/3. That means that x is equal to r sin minus 2/3 or r sin 4/3. And it's at this point that we're going to use the definition of r sin. So that means that x is equal to this big expression here, the log of that, or x is equal to the log of this big expression here. Simplifying those gives us that. And simplifying those gives us x either equals the log of minus 2 plus root 13 over 3, or this last one simplifies a great deal, and you just get x equals log 3. Okay, that gets us to the end of the lesson. If you've got the textbook, then turn to page 13 and have a go at exercise 1D. Thank you very much for listening, and cheerio.